So this is back to the beginning of the 7.3 notes packet. The logarithmic functions I've separated into two videos. So if you're looking for the graphing of logarithmic functions, you have to go find the other video. This one's just going to discuss the manipulation between a logarithmic and exponential equation. It'll discuss a little bit about inverse properties and then how to find inverses of logarithm functions. But it's not going to discuss graphing at all. So make sure you're on the right video before you waste the next 10 minutes, 15 minutes. Alright, this here we're going to definitely do in colors in the classroom, so if you have colors you might want to pause the video and get them out. This is called logarithmic form, and it has the abbreviation of a logarithm. Wow, good handwriting. This is logarithmic form, and this is exponential form. So the lessons before this one were all discussing there we go. We're all discussing exponential functions and how to graph them and how to use them in application questions. It seems a little backwards here, right? We wrote down y equals b to the x power. It's a very basic form of an exponential function. The idea is we're going to understand that a logarithm function is simply the inverse function to any exponential function. So just like an exponential function has a base, a logarithm has a base as well. And on your calculator, there's what we call a common logarithm button, and there's also called a natural log button. We'll discuss those later on. So our first task is to be able to transform between the logarithmic and exponential form. So if you have any colors, what I'm going to do is I'm going to color the b's in blue, seems appropriate, and you're to recognize that they're going to be the same value. And then I'm going to color the y's in green. Apparently I can't write today, sorry. And then the x's in red. So these are saying the same thing. Turns out logarithmic form, not real great for my brain. So if I'm trying to do some evaluation, I think better in exponential form, because guess what, guys? I don't have logarithms memorized. I'm not a computer. I do have some. I'm not a supercomputer. All right, so here we're going to take this logarithmic form and we're going to rewrite it into exponential form. So I can tell from my color coding here that x is what we call the base. It's like a little subscript below the line of the logarithm. It's indicating what type of logarithm you have. So it's a base x, which is weird. And then 5 is my answer over here. And then 32 is what is inside the logarithm function. So the other way I read this is I write logarithm of base b. And then inside the logarithm is some function. Alright, sorry, I was interrupted. So let's see if I can figure out where I left off. So we were trying to write number 1, which is in logarithmic form, into exponential form. So I identify who the base is, which is x. And then I raise it to the new exponent power, which is the answer of the logarithm question, which is weird. And it's supposed to come out to equal what was inside of the logarithm, which was our 32. Now, your job today for this section is just to rewrite into the alternative form. So x to the 5 equals 32. That's what I want to see for this question. There's a lot of muscle memory associated with rewriting formulas. So just what I do is dyslexia. So I find the base and I write that down as a base. And then I basically just flip-flop the other two numbers. So same idea here. If I can identify who the base is. Oh, I know where I left off before I got interrupted. I was trying to come up with this formula. Log base b. I call this thing inside here the number. It's a hashtag symbol to you children, but it's a number symbol. And then equals what I call the answer of the logarithm question. So base to the answer equals the number is the way that I kind of mentally say the rewriting formula to me. Anywho, back to this question, the base is 5, so I'm going to write that down as my base. And then the 1 and the 0 will flip-flop. So the 0 becomes the power. And then it equals what was inside the number that was inside of the logarithm to begin with. So equals 1. So your job, just rewriting the formula. Number 3, my base is a 10. And then this 1 becomes the exponent. And it equals what was in the logarithm, which is the number 10. Notice everything we've written here, it makes mathematical sense. These two last two examples make perfect mathematical sense. 5 to the 0 is 1, 10 to the 1 is 10. And this one we could solve. X to the 5th power is 32. If I was asked to continue on and solve or simplify, the answer to this one would be x equals 2. But that's why I like when they're numerical, because I can tell if I've done them right. So we look at number 4. The base is a 10 again. And then the negative 1, the answer to the logarithm, becomes the exponent. And it's supposed to equal what was in the logarithm originally, which was 0.1. You can just write 0.1 if you'd like. But 10 to the negative first power is 1/10, which is the decimal 0.1. So that makes lots of sense. Same idea here. My base is a 1/2, which I would write as a vertical fraction because I don't like the other kind. Use parentheses around that base though. The negative 1 becomes my exponent. And then the 2, which was in the logarithm function, becomes my answer. Now this question is a little bit tricky because they don't give me an answer. So you could say equals question mark, or you could say equals x, but this is how we're going to start thinking about logarithms. Log of something equals, and that's my question. So this is a base b. I don't know what it is, but I'm raising it to some mysterious power, and it's going to come out equaling the number 1, which was in the logarithm. Now think about this, guys. What could my power possibly be? If I raise it to a power, whatever power that is, and it comes out to equaling a 1, well, the only power that makes your answer, forces it to be 1, is if your power is 0. So keep that in mind. Right here, the base is a b, very random, and it equals some mystery number. And this exponent problem is going to come out to an answer of b as well. So let's use our rewriting technique. Base b to some mystery power, don't know what, equals b. Think about your power properties here, guys. B to some power coming out to a b again. The only way that would work is if this mystery power was a 1. So what we're going to be doing next is we're going to be evaluating logarithms in our noggins for a lot of them, and then eventually we're going to have to settle on using technology because our noggins can only go so far. So my brain does not think in logarithms, so I have to always think of these in terms of exponent problems. So I start off by saying, what does this equal? And then I use my rewriting my formula because I can't think of a logarithm of base 3. So base 3 to what mystery power will give me an 81? So I have a chart of values, or I test some stuff out on my calculator. Turns out that that power is 4. So yes, if you have powers memorized, this is going to go a lot smoother. If you don't, don't use that as an excuse. You have a calculator at the very worst. And you have various charts of values somewhere in your notes, so if you need another one, I'll get you another one. Right here, base 5, raised to some mystery power, don't know what. It's going to come out to 0.404, excuse me. Now, the first thing I'm going to do is 0.04. If you need to hit math enter, that's fine, but that's the same thing as 4/100ths, which is 1/25. So I think, how would I take 5, raise it to an exponent, and get an answer of 1/25? Well, to change a 5 to a 25, I'd have to square it. But to take a 5, a whole number, and flip it down to a fraction, to flip it to the denominator, doesn't your exponent have to be negative? So if you don't believe me, test that out on your calculator. What is 5 to the negative 2 power? It's 0.04, which is 1/25. All right, so this is going to be fun. All right. Got to remember exponent rules and everything. What are you doing, Pearson? All right, 1/2. Raised to some mystery power, don't know what yet, but it's supposed to come out to equaling an 8. So we have the same issue with, I'm going to start with a fraction. I'm going to need to flip it around to an integer, so I'm going to need my exponent to be something negative. That'll flip it. But then if I take a 2 and raise it to a power to make it an 8, the power I'm looking for is a 3, a negative 3 to be precise. If you don't believe me, try that on your calculator. 1/2 or 0.5 to the negative 3rd power. Make sure you use parentheses if you wrote 1/2. That's how you make it flip around to an 8. All right, and this is like the trickiest question, I think, on this section. If we were doing this in class, I'd probably let you guys guess and check for the rest of your lives until someone came up with the answer. But the base of 9 is being raised to some power, and it's got to come out to a 3. So usually kids guess things like 1/3, -3, -1/3. They try all sorts of things. And you got to think about the fact that we have an integer and still an integer. So I don't want a negative exponent. So then you're going to try some things. And eventually someone's going to stumble upon the right answer, which is 1/2. The 1/2 power, remember, is the same thing as the square root. And what is the square root of 9? It's a 3. So if you think about where you want to be, I want to take a 9 and change it to a 3. The mathematical relationship between those two would be the square root of 9. Now, for our calculator, you have a common log button. This is the common log, which is base 10. You have a button on your calculator that uses that particular base logarithm. That's because it's used so commonly in math that they gave it its own quick key button. And then you have my favorite, the natural logarithm. So the natural logarithm is base e, which is a number. We learned about him in the PERT formula from before. E is roughly 2.718. It's a weird irrational number. So if you have a base e logarithm, they shorthand that as ln, which you're going to see me write a cursive ln of x. I do not want to see like this. I get that a lot from kids because they think it's an I. It is not an I. It's a lowercase l. To avoid issues of kids not writing the right thing, could you just start, I know you all know cursive, write it in cursive, ln. Alright, so here you have the common log. So on your calculator, you're just going to write common log 5. And this is not anything pretty, because 10 to what power gives you a 5? Like, you could be guessing for a long time, right? So we just simply type common log 5. So common log button of 5. And it's gross. It's 0.69897, blah, blah, blah. So round to whatever they want. Do they say anything? It doesn't say, so we'll say 0.7. 0.70, we'll go hundredths place. So common log 21, you just type that on your calculator. Let's go to 14. This is the natural log of 0.1. So this time, just make sure you're pressing the right command button, guys. We have a natural log. This is the natural log key. Natural log of, I forgot what it was. 0.1. Got like a goldfish brain today. 0.1, which is negative 2.30. So definitely not something I would expect you to get off the top of your head. Even I don't know the answers to these. Some of them are not, you can't do them in your brain, so you have to use technology. Or back in the day, they'd use like a table that people derived the functions. Ooh, good times. All right, we have, this is a pretty boring question, I'm going to skip it. We have some inverse properties to talk about real quick. So if you have a logarithm of a certain base, and then inside of that logarithm is an exponential problem with the same base, okay? That's the key here. If you have the same base, that means they end up canceling each other out, and then this x doesn't have anything holding it up, so it drops down, and you get an answer of x. So very similarly here, you have the same base of an exponential, and up in this exponent is a logarithm with a matching base. So again, these cancel each other out, and this x drops down, and you just get an x. So logs and exponential functions, because they're inverses of each other, if they match bases, they end up canceling each other out. So here, log base 6 of 6 to the third power, the log base 6 of 6 cancels. This 3 has nobody holding them up. 3 drops down. Ooh, the answer is 3. 5 to the log base 5 cancels. The answer is 13. This is easy, right? These are really important properties coming up. This one tricks kids because e to the natural log of 15. Remember, natural log of 15 is the same thing as a logarithm of base e of 15. So e and natural log are also inverses of each other, so this is a 15. And then this one's weird. You don't know this yet, but if you could please throw this 2 up in the exponent and call this 3 squared. Then the e and the natural log will cancel, and you'll get 3 squared, which is a 9. We'll talk more about that property later. Sorry about that. All right, here. Leave the 5 for a moment. Let's talk about natural log of e to the third. Natural log and e will cancel. The 3 is going to drop down. So what you really have is a 5 times 3, which is going to give us a 15. And then, this one always eludes children. This is log 2. It doesn't seem to have a base. But if they just write logarithm, we're to assume that they meant the common logarithm, which is base 10. So this is really 10 to the log base 10 of 2. 10 to the log base 10 cancels. So the answer is just a 2. Gosh, I don't think my handwriting is getting any better today, guys. These properties are awesome, but they only work if you have matching bases. So what we would have to do here on number 23 is we're going to have to rewrite 9 so that he is a base 3. So think of a way to rewrite 9 as a 3. 3 to the what power would be my question there. 3 squared would be the same thing as 9, right? So then I want to think about my exponent properties. 2 to the x power, if I were to combine these, I just multiply them together. So this is really log base 3 of 3 to the 2x power. And then look at this beautiful stuff. Cancels, the 2x drops down, and that's our simplified answer, 2x. It's a tricky question, but do expect one of those. All right, remember how to find inverses. We switch the x and y, and then we solve for y. And then remember, we're supposed to be like using this notation, or sometimes we use this notation. All good things to think about. So remember, this is our color-coded formula for how we switch things around. The easiest way to come up with an inverse for this is just to remember that a logarithm and an exponential problem are just simply inverses of each other. So I'm not even going to go through all the steps of finding an inverse. I'm going to save that for another time. We have to learn something about exponentiation first. I'm going to call this the inverse of y. And I know if it is a logarithm, I need to rewrite it as an exponential problem. So I figure out who my base is. My base is a 3. And then I raise it to the x power. That's the inverse function, okay? I'll show you the algebraic way to find it. So if you switch the x and y, and then you think about the rewrite formula that we just talked about. Base 3, x is the answer. It's backwards though, isn't it? Whatever, we can work with that. Equals y. So if I rearrange it solving for y, I'm going to use this formula, except I use y instead of n, so that's confusing. Y equals 3 to the x power. So usually this is where kids go, wait, I feel like this way was a lot easier. Yeah. If you notice, you have a logarithm, a very simple one. The inverse to a logarithm is just simply the exponential buddy of. So here, in this next question, this is a common logarithm, so it's a base 10, right? So his inverse is just going to be an exponential of base 10. So 10 to the x power. So without doing all that work and rewriting, if you just know the relationship between exponential and logarithmic, you're good to go. This one's a little more difficult though. This one we're going to go through the algebra. I'm going to switch the x and y. And instead of natural log, I'm going to write log base e. Alright, and we're supposed to solve for y, aren't we? This would make so much more sense if you guys knew how to solve for, how to undo logarithms in a moment. Rewriting formula. My base in this problem is an e, right? So I'm going to write e, and then to the x power equals what was in the logarithm, which was this y plus 1. But we're not quite solved. We have to subtract the 1 still. So this becomes, I'm going to flip it around, inverse function is e to the x power, and then a subtract 1 after the function. Okay. That was trickier than anything I'm going to give you in Algebra 2. The ones I give you are more like 24 and 25, where as long as you could figure out like the logarithm and the exponential ones are inverses of each other, you're good to go. Alright, and that is where we're going to end this other part of the lesson. If you're looking for the graphing, you have to go find the other video, so hopefully you didn't just waste 18 minutes of your life. Good luck!